Okay, class, hope you had a good Thanksgiving. I'm going to bang out these last two videos for week 15, um, and then we're pretty much done. So today we're going to talk about game theory and static games. So we'll hop right into it. If you recall, last class we talked about the competitive spectrum, which is just words for how many firms are competing in a market. And the simplest form of this is just so basically we studied perfect competition and we studied monopoly, and we kind of briefly talked about monopolistic competition. The results aren't too different from monopoly for that, but for oligopoly we have a really rich set of solutions that we could talk about using game theory, where the strategic interactions or the decisions of one firm affects the profits of another firm. And so the simplest kind of form of this is a duopoly, where there's only two firms, which is more than a monopoly, but not far enough to be perfect competition. And so it's kind of like this very right side of this oligopoly dot. And so we're also going to assume there's no product differentiation. And again, we want to know about the strategic interactions between firms and how they decide and what to do when their decisions affect other firms. And so this is game theory, and this is just like John Nash in A Beautiful Mind, if you've ever seen that video. And so hopefully you've read this, and I'm going to get to this little Wayne quote because I like it a lot. And so what is game theory? It's just a mathematical, scientific study of games. And so games can really mean a lot of things here. And so checkers, chess, pricing decisions, prisoners, and bargaining, and many, many more. So I'll note that computers have solved checkers. You can't beat a computer in checkers anymore. Chess is kind of different because chess is hard. There are many, many ways for the board to be arranged. And so economists have just borrowed game theory from math to analyze strategic interactions of business that we care about in economics. And so what can be considered a game? It's just literally anything where the decisions of some players affect the outcomes of other players. And so typical outcomes that we think about are utility, profit. Some other ones would be like years in jail. A simple one is like whether or not you just won the game of checkers or chess, which if you win, you have higher utility. And so, but this encompasses like so many scenarios. All there really needs to be is a strategic interaction. So these are really broad and helpful for thinking about the world. So games are just competitions between players in which each player is aware that the outcome depends on all the other players. And so oligopoly pricing decisions is what we're going to talk about today in the next video. And all we have is that each firm influences the price and hence the profit of other firms. And so that's what we're going to talk more about, but I just want to give you kind of a breadth of all the applications in economics that this can be useful for. So anytime you're setting a price, a quantity, how much you're advertising, where there's bargaining between unions and managers, because what the union does affects the managers, and what the managers do affects the union. Employers and employees are kind of the same deal. Polluters and those damaged by pollution, home buying and selling, between parties with limited information. So this is where you get like the Lemons of George Akerlof. This is a really famous study using game theory because you have very limited information about the quality of cars, and then bidding and auctions, which we'll get into. And even outside of economics, political scientists and military planners also use this. So a famous example relates to the doctrine of nuclear warfare, which hopefully we aren't affected by thanks to this strategy. But this is most well known during the Cold War between the United States and the Soviet Union. And what they had was mutually assured destruction, which is if you nuke us, then we'll nuke you and everyone will be dead. So just don't nuke us. And so in this scenario, it's very obvious that the outcomes of the Soviet Union depend on the actions of the United States, and the outcomes of the United States depend on the actions of the Soviet Union. And it's actually also referenced in Sun Tzu, the most ancient book on warfare, in the art of war. He says, "On desperate ground, I would proclaim to my soldiers the hopelessness of why is this in the way? I feel like a boomer. Of saving their lives." And so I'm going to talk more about that at the end of the next one. But and political scientists use this too to study strategic interactions between political offices. So you can think about like how Congress, which has the ability to spend and tax, interacts with the Federal Reserve, which has the ability to set interest rates. And so that's like kind of a famous application in political science in this. And so the elements of a game are just you have one, players, people who are involved competing with each other. You have strategies, so it's really important to differentiate between what a strategy and action is. A strategy is a plan specifying an action that a player takes at each stage of the game based on the information available for every possible potential situation they find themselves in. So strategy is like an entire battle plan, as the book calls it, for like everything that could happen. Whereas an action is just like a very isolated, like, I do this one thing. So like in chess, a strategy, you'd have to like map out what you would do if your opponent did every single thing. Whereas an action would be like, at stage one, I move my pawn to bishop 4 or whatever. Yeah, I've been watching Queen's Gambit. Hope you have too. It's really good. And then payoffs. So this is players' valuation of the outcome. For businesses, this is pretty simple. Like the outcome is profits. For individuals, you have utility. So higher utility is better. And then, you can have other specific situations like years in prison, which are kind of undesirable. And so it's really important for something to be a game and be able to be, the subject of game theory, that there's players, strategies, and payoffs. And so some additional elements of games are you can have static games, which we're tackling today, where both players move at the exact same time without seeing what the other player does. This is a simultaneous game, or a dynamic game, which is where players move sequentially or repeatedly. And so this is like chess, checkers, and lots of other situations where you can see exactly what your opponent did in the action before. And so there's a lot of study about how information comes into play. So if you have complete information that says, the payoffs of all players is known to all players, we're just going to assume this throughout. And then when you have imperfect information, you don't know the other person's moves, and you can really start to model some more complex situations with that. We're not going to do that. So I want to start out with simultaneous, static, normal form games. And so what we have is two players. We have two airlines, American Airlines and United Airlines. And both of them have to decide how many passengers to take on a specific plane route. And so we're going to use this kind of 2x2 matrix. It doesn't have to be 2x2, but we will just use it for simplicity to model this game and to write out all the players, their potential actions, and their payoffs. And so in this matrix, now you can see that we have United Airlines actions here on the vertical axis and American Airlines actions here on the horizontal axis. And so from there, we're like, okay, Ben, we know who the players are. What are their strategies? Okay, well, both of them can fly either 64,000 passengers, which I just had 64, or 48,000 passengers, which is 48. And so it's important to note kind of that our strategy space is symmetric here, meaning that the firms have the exact same strategies. They can do 64 or 48. And so we have 4 situations which can happen here. They can both do 64. They can both do 48. United does 64. American Airlines does 48. Or American Airlines does 64 and United does 48. And so those are the 4 possible combinations of actions that our players can take in this game. And so the last thing we need to do to make this a game which is analyzable by game theory is we need to know their profits. And so what I've done here is I've put their profits in these matrices, and their profits are a function of both what they decide, how many flights they decide to fly and how many their competitor decides to fly. And so those both affect their profit because it affects the price of their services. So taking a minute here, in 1, we have if American chooses 64, United chooses 64, the profit's 4.1 for both. If American chooses 48 and United chooses 48, they both get 4.6 million dollars. And if A chooses 64 and U chooses 48, then A 64, U 48, then we have United Airlines making 3.8 and American Airlines making 5.1. Shouldn't be too hard to see that. We can see that American Airlines is moving more people, and so they're selling more, presumably at the same price. And then the opposite box up here is kind of the same thing but flipped. And man, this thing's annoying. It's important to note that in all these boxes, I have the profit of United to the left because they're on the vertical axis, and I have the profit of American as a right number because they're on the a horizontal axis. And this is just the way it's done to keep everything straight. This is like a convention in game theory. You don't have to follow it, but if you don't, then you definitely need to specify this, which one is which number is which firm's profit. Okay, cool. So what happens? Like, great, you like wrote out the potential payoffs and the strategies. But like in economics, we're really interested in like predicting the behavior and knowing like what is the best like optimal path for businesses to choose. And so kind of a lot of people think just like looking at this that like 4.6 should be what the businesses get both, because it is like kind of the maximum output. This one is a total of 9.2, whereas this one is like 8.9, and this one 8.2, and this one's 9.2. And so everyone's like, oh, well, they're just getting the bottom right. But we've got to remember that these firms are not trying to maximize total profit in the market. They're trying to maximize their own profit. So they really don't care about the sum of the payoffs. They really only care about their own. And so for this, we need to think about strategies that the firm can play. And so a really important terminology here is a firm can have a dominant strategy, which means no matter what, they should always do the same thing. And so a strategy that produces a higher payoff than any other strategy for every possible combination of its rival strategies gives you a dominant strategy. And so you're basically best responding to the other firm's optimal decision making. And it sounds kind of complicated. And it does take some practice to identify a dominant strategy, but it doesn't require that complicated of math in the setup we currently have. And so I'll expect you to be able to do this. And so a Nash equilibrium, we say, is a set of strategies that if all the players play these strategies, no player can get a higher payoff by choosing a different strategy. And so this is a really important concept of how we find the equilibrium outcome of strategic interaction between, in this case, two firms, but in more general case, two players. And so what we need to do is let's just consider what United Airlines is thinking. So one thing that could happen is American Airlines could choose to have 64,000 flights. And so if American Airlines chooses 64, then United Airlines needs to choose between 64 and 48. And remember that their payoff is the one to the left. This is essentially asking, do they prefer a 4.1 or 3.8? And obviously they would prefer a higher profit. So what happens is we underline the payoff of United Airlines in that column here, and we say we would expect United Airlines to choose 64 if American Airlines chooses 64. Now, if American Airlines chooses 48, then the best decision for United is either 5.1, which they get if they choose 64, or 4.6 if they choose to run 48 flights. So obviously they'd rather have 5.1 million in profit. And so we underline 5.1 and we say that, okay, United Airlines' dominant strategy is to choose 64. And so you'll notice that both the strategies and the payoffs are completely symmetric. And so what happens is American Airlines chooses between 4.1 and 3.8. If United chooses 64, they'd rather have 4.1, so we throw an underline under that. And then United Airlines would rather have 5.1, or American Airlines would rather have 5.1 rather than 4.6 if United Airlines chooses 48. And so we can see here that American Airlines' dominant strategy is also to run 64. And so what is our Nash equilibrium? What we expect to happen most of the time is American Airlines chooses 64 and United Airlines chooses 64 because it's both of their dominant strategies, and it's impossible for them to do better by deviating, knowing what the other firm's optimal strategy is also. And so we know this is a Nash equilibrium because both of the payoffs are underlined, which I showed you how to do in the last couple slides. And something special about this game that you notice is that there's only one equilibrium, but there's no need for that to be the case. Especially, it's more likely to happen if some of these things are tied. Then you can have multiple Nash equilibria. So something that's kind of dissatisfying to people about this being a Nash equilibrium is that they're not maximizing their total profit or the cumulative profit in the market. They've got both getting 4.1 million, where if they both could coordinate to 48, they would get 4.6. But notice, if United chooses 48, then American is still going to run 64, and United loses profit, and American Airlines gets more profit. And so we don't ever actually end up in this maximal profit square. And so this is a kind of a profound result. And it's a kind of specific case of what we call a prisoner's dilemma in game theory. So I'm sure you've all seen well, I'm not sure you all have, but in cop shows, they have, they arrest two people and they know they're kind of like working together for a crime. Then what they do is put them in separate rooms. And so by being in separate rooms, these guys don't know what the other prisoner is doing. And that makes this a simultaneous game where the prisoners have to choose to either confess or lie. And you notice that actually in this case where, the prisoners would like to both be able to lie and coordinate into here where they only both serve a year, they're actually, their dominant strategy is to confess. And that's why law enforcement does this. And so they both end up in jail for years. And so these simultaneous games have a lot of different iterations based on kind of what the optimal outcome or the Nash equilibrium ends up being. And kind of a different game, which you've also probably heard of, is Chicken, where the two players here are James and Dean, and their actions are either swerve, be a chicken, or keep going straight and be tough. And this is like when you have like two cars like driving right at each other, it's called chicken, and the person who swerves off first is chicken. Could be planes too. Like in Pearl Harbor, there's a really nice scene with this. Not nice, but exemplar scene. And so in this case, then you should try to go through and practice and figure out what are the Nash equilibria or equilibrium of chicken. Anyway, that's everything. So I started to introduce game theory as a way to study strategic interaction, which is exactly what an oligopoly market is, which is a market with few firms, where everyone's profits depend on the actions of the other firms. And so we've learned how to represent these interactions and payoffs in a simultaneous normal form game. And then we've learned how to predict the equilibrium outcome by finding dominant strategies, which is really cool. And it can be generalized to a lot of things like soccer penalty kicks or roommate relationships. It's really like a very generalizable topic that I'd be interested to talk to you more about. Anyway, that's all I have for this lecture. And in the next lecture, we'll be adding dynamics to game theory, where there's an element of time where each person can observe the other person's moves. Anyway, thanks for listening.